Okay, so, you guys ready? We're going to talk about categorical variables today, so it's kind of fun that these chapters sort of review the other stuff that we did a little bit, so it helps you review for your final. So, back in chapter 4, a long time ago, we talked about looking at were two categorical variables related. We did some examples like, is the likelihood of divorce higher for smokers versus non-smokers? Remember that? Like, we did like a chi-squared thing. We found these expected value things. Or are you more likely to get cancer if you eat bacon than if you don't eat bacon? Apparently you're not supposed to eat bacon, which is very sad. So, in this situation, the stuff we're going to talk about today, we use categorical variables that consist of group or category names. And the thing that is important here is that these things don't necessarily have any logical ordering. Sometimes they do, but categorical variables don't have to. There's no logical way to order you guys by eye color. I mean, maybe Roy G. Biv order, but nah. A two-way table displays the counts of how many individuals fall into each possible combination of categories. Do you remember those tables? Okay. This type of table may also be called a contingency table. Do you remember how to find row percentages? So you look at a row and you say, okay, well, how many people in this category in this row feel this, are in category 1, how many people in row 1 are in category 2. So they're based on the total number of observations in that row. And column percentages are based on the total number of observations in a column. So the group that is row 1, the group that is row 2, or the group that is column 1, the group that is column 2. And you look and see how the opinions differ among those groups. Now, this next thing is just review from what we did last time. So when you're looking at two categorical variables, we're interested in finding whether there is a relationship. And this question, we used a chi-square test. And the thing that we said was if our chi-square was big enough, then we were able to reject that null hypothesis. Do you remember how big the chi-square had to be? 3.84. Does that ring a bell as a number? Like, kind of like, yeah, exactly. That's what these 5 steps are. This was the first hypothesis test you did, but it was a long time ago, and therefore, it kind of trickles away as time passes. So your null hypothesis always was that the two variables are not related. So, for example, smoking is not related to divorce rate. And the alternative is that they are related. And for these chi-square tests, HA is always two-sided. I just spelled sided wrong, obviously, it's Monday. So, and the only way to change that is actually to do a different test, like do a z-test. If you're going to use this chi-square thing, you're only testing two-sided stuff. So the second step is you find your test statistic. And in the past chapters, our test statistics have been z's or t's. In this one, it's a chi-squared statistic. And do you remember this whole observed minus expected squared over expected thing, like vaguely? Okay, that adds up and makes this thing called the chi-squared statistic. It's kind of like a squiggly S. And the way that you find the expected values is you do the row total times your column total divided by the total number of observations in your table. And one important thing is don't round those expected values to whole numbers. Use 2 decimal places. That's your book's standard. It's always better if you use more, but let's just follow the same standard. Okay. The next thing you do is you figure out how likely is my p-value. And to do this, you use a chi-squared distribution. Did you guys grab that table up in the front of the room that also said it's a chi-squared distribution with the notes? Okay, so you guys remember that if the chi-square was bigger than 3.84, then you could reject a null hypothesis, right? In all the stuff that we did in chapter 4, the degrees of freedom was 1. So look at the degrees of freedom being 1. go over, you see how then you go over and you have these numbers in the table, those are your chi-squared numbers. Go to 3.84. What p-value does that correspond to? 0.05. To see why that was the boundary chi-squared? Okay. So now we're going to do this more generally today, where we don't just have tables that have 2 categories and 2 categories. We have tables that have like 3 categories and 3 categories, so things that are bigger. And the way you find degrees of freedom is you take r minus 1 times c minus 1, where r is the number of row categories and c is the number of columns, not including the totals. Does that make sense? Like just including the sort of raw data. And so because of this, since all the other stuff we did was 2 by 2, in chapter 4, df was equal to 2 minus 1 times 2 minus 1, which equals 1. I know you were also very unimpressed that like 3.84 isn't that big of a number, but you see how as your degrees of freedom get bigger, the number that you have to get to that 0.05 threshold also increases. Okay? So the 3.84 boundary is only true if you have a 2 by 2 table. Otherwise, it's a bigger number, which is determined by these things. Okay? And then decide whether, so you're going to use this table to find p-values now. I'll have to give you like a whole crap ton of tables for your final exam, because you have so many. And then the last step is decide whether the result is statistically significant based on the p-value, choose a significance level, and what's your standard level? 0.05. And then give me a conclusion in context. You reject H naught, fail to reject H naught, and then what can you say after that? Okay. So in a nutshell, that's kind of what we're going to do today. Since we have to use this table, let's first practice using the table, right? Often, I'll also tell you how to use technology to get the values exactly, but you might have to give me a range of values like on homework or a test if all you have is the tables. We'll do both. So chi-squared is 3.84, degrees of freedom equals 1. You can find this in the table. So go to df equals 1. Go over until you get close to 3.84 or exactly to it. And what do you find? P is equal to 0.05. Does that make sense where that came from? Yes.
Since they are two-tailed, when we're doing like hypothesis tests or whatever, do we have to multiply that by 2 or anything?
Nope,
Or just
it's already that number. Yep, it's already been multiplied by 2. Yep. Okay, chi-squared is 2.28, degrees of freedom is 9. If you look at your 9 row, what is the smallest number in there? 8.34, right? So how does your p-value, so what happens as you go from left to right? What happens to the p-values at the top?
It's small.
They get small. The chi-squared goes up, but the p-values in the top are getting smaller, right? Right to left. So what would happen if your chi-square was even smaller than that 3.84? How is your p going to relate to 0.5? It's going to be even bigger than 0.5. So if all you had was the table, this is the conclusion you would give me. To find that exactly in Excel, so here's my Excel directions. You go into a cell and you type equal chi dist. Preferably while drinking chai tea.
Yes.
Yes, okay. And then you put in your chi-squared number and your degrees of freedom. So in this case, that chi-square number we put in is 2.28. You put in df equals 9, and you get 0.986. You would really fail to reject H naught in that case. Does that make sense?
Yes.
Yes? Okay, thanks, guys. I know it's hot, which delays your response time, but, no. All right, how about this guy? So chi-squared is 26.3, just a little bit more than a marathon. R is 2, C is 3. So first thing you have to find is your, which is R minus 1 times C minus 1. So what's that? 2 minus 1 times 3 minus 1, which is 2, okay. And you look at your degrees of freedom 2, and And you look for 26.3 and you're like, well, geez, that's not there. So it's to the right of 13.82, correct?
Yeah.
So your p-value is, how is it related to the 0.01?
Less than.
Less than 0.001. And if you give this to Excel, and you say equals chi-dist 26.32, it tells you it's 0.1234519. And is that less than 0.001? Yeah. But would knowing your p was less than 0.001 be enough to make a conclusion? Yeah, exactly.
A lot of zeros.
Lot of zeros, exactly. Yeah, it's really small. Occasionally, if you get small enough, like one of the questions we're going to have an example of today, Excel just gives up and says it's 0.
That happened, the homework said that something was 0.
Yeah, it happens. It said it was effectively 0 because it
Yeah.
was really close enough to just not matter anymore. This probably also is close enough to not be, to just be close enough to 0 to be.
I don't know what you're.
All right. So in the 2008 General Social Survey conducted by the National Opinion Research Center at University of Chicago, participants were asked whether or not they favored the death penalty and then whether or not they thought marijuana should be legal. And we're trying to figure out, is there some pattern here? Do people that favor the death penalty also favor marijuana legalization? I don't know. Who knows, okay?
That would be opposite.
Yeah, or would people that favor the death penalty be opposed to legal marijuana? I don't know. I mean, so this was also done a while ago, well, 8 years ago, so maybe stuff has changed. But let's first find column and row percentages to see if there appear to be differences between the groups. Does that make sense? So first we'll do row. We have the favor, you have to write a little small, I'm sorry about this, oppose, legal, not legal. Okay. All right, so so if you're looking at a row percentage, what's the total you take stuff out of? At least for the first row.
7.
The 774. So of everyone that favors the death penalty, what proportion favor marijuana legalization?
313.
Yep, 313 out of 774. And that works out to be 40.4%. And I think that if you know that that's the pattern, the not legal is also easy to get, right? It's 59.6%. And across the row, what should they add up to? 100. Good. Okay, of the people who oppose the death penalty, how would you figure out the proportion who support marijuana legalization?
165 over 412.
Which is about 40%. And then making the other one 60%. So does that suggest there's any difference? Do they appear very,
Well,
well,
like a ton,
but,
well, I guess
like,
no.
does the
I was looking at it wrong.
the favor group differ from the opinion of the
Yeah, I was
opposed
looking
group?
at it
No,
wrong.
you're looking at the, yeah, exactly, I see what you're saying though. But the point is that this row isn't different than that row. Yep. There is a difference between the legal versus not legal camps, that's definitely true, yes. Okay, so that's the row percentage. Just look at the columns and see if that's any different. So favor, oppose, legal, not. And this time, what's your totals? Instead of using the row totals, you use the column totals.
313 divided by 478.
Yep, 313 out of 478. That turns out to be 65.5%. Meaning the next one down is 34.5%. $461 out of 708. I got that was 65.1%. And this is Yeah. Does there appear to be a difference? I would say there doesn't, right?
I keep looking at the wrong way.
Yeah, I understand your like sort of confusion. But you need to say compare row 1 to row 2. Do those appear to be different? No. And then here, does column 1 appear to be different than column 2? No.
Yeah, what I'm doing is I was looking at.
What you were doing
is there
is
a
you're
difference
looking at,
within
like-
the row?
Yeah, exactly, which there is, but that's not the question. The question is are these things related somehow? Are people that, if you favor the death penalty, can I predict if you favor marijuana legalization? Does that make sense? You can, certain behaviors tend to happen together, right?
Mm-hmm.
This one doesn't seem to be like that. So there doesn't appear to be a relationship. Gesundheit. Between death penalty opinion and legalization opinion. But let's actually do a chi-squared test to figure it out, to check for certain. Okay, so when we do this chi-squared test, so first thing we should do is state our null and our H naught and our HA. So H naught is that there is a relationship, is no relationship, nothing going on between these two variables. So the two variables are opinion on the death penalty and opinion about marijuana legalization. Does that make sense? And the H naught is that they're not related. So opinion about OUT, the death penalty and opinion about marijuana legalization are not related. And then HA is the opposite, the two-sided opposite of that, so that they are related. Okay. Does that ring a bell? Most of the work is in finding the chi-square statistic. And to do that, which is part C, you have to first find the expected values. And that's found using the row total times the column total over the, do you remember? Total, exactly. Okay. So for this first box, what would be my row total that I would have? So this first box,
774.
774. What's the column total?
478.
And what's the total?
1186.
That gives you 311.95. How about the next one? What's your row total?
774.
Uh-huh. Column?
708.
Yep. Over?
1186.
Yep. And that is 462.05. Do you get the idea? Okay, the next one, just to save us some time, is 166.05. What would they be anyway? It's not that it take that long. It's, row total is now,
412.
times 478 over 1186, yep. And then 412, 708, 1186. This is 245.95. So these are the values that you would expect to see if H naught was true. And one way to conclude that H naught is false is if they're kind of far away from your table of values. Are these very far away from the actual values that you have? Like, is 311.95 very far from 313? Yeah, and is 462.05 very far from 461? That suggests that probably nothing is actually happening here, okay? But the way you verify that is you use this chi-squared test statistic, and that chi-squared is the sum of the observed minus expected squared over expected. Does that ring a bell? And I'd like you to show me your work on this so that I can verify that you understand the formula and not just that you can punch the right buttons in your calculator, because it just takes, if you miss one number and you get the wrong answer without seeing your work, I have no idea how much you know. So and just go in the table, I'm gonna go across the first row and the second row. So what is the first observed value?
313.
And what did you expect to see there?
311.95.
Squared over 311.95. Okay, and then next row over, what did you observe?
461.
Minus, you expected to see
462.
squared over 462.05. And then just keep going. You observed 165, right? Minus 166. And then finally observed 247, expected 245 over. Okay. So show me that, and then tell me what you get when you punch it in a calculator, and you get, at least I got 0.017. Remember that chi-squared had to be big to reject your H naught. This is a 2x2 table, so what's our big cutoff? So is that big enough? No, definitely not. And let's actually even use, so we have now this table, let's use the table to get the p-value. So how many degrees of freedom do you have? How many rows do you have? 2. How many columns do you have? 2. So degrees of freedom in this case is 1. Okay. Table. So if your chi-squared is 0.017, what's the smallest chi-squared in this table for degrees of freedom 1?
0.0.
So do you agree that your p is bigger than 0.5? Okay. That's good enough. Because if your p is bigger than 0.5, can you make a conclusion about your null hypothesis? You can't reject it, exactly. Okay. So your final part is that you failed to reject H naught. Okay, that doesn't mean that, H naught is true. So it just means you don't have enough evidence to conclude HA is true. So here's the way to write that. There is insufficient evidence to conclude that there is a relationship between opinion on death penalty and marijuana legalization. So what we're going to do today, with the next example, we're going to extend this idea to a table that's bigger, just has more categories in it. That's all. So, for example, here we have a table that has data from typical grades that 12th graders had and whether or not they always wore a seatbelt or kind of rarely wore a seatbelt. And we're trying to say is their relationship here. Do you think that, do the numbers suggest that there is relationship? I mean, I know they're kind of big, but look at the total number of A and B students in proportion that wear their seatbelts versus the lower grade students, and you see how that might be actually quite different? So what's our null hypothesis then? There's no relationship, yet, between grades and seatbelt use. So there is no relationship between grades and seat belt use. And what's HA? There is a relationship, yep. And the only difference here is that when we find the expected values, in the previous example, how many expected values did we have? 4. Does that make sense? Here we're going to have an expected value for every single one of them, maybe 6 of them. It just gets tedious because there's just so many of them. Does that make sense?
Yeah.
So that's what we're going to do. We're just going to find those. And then we're going to do the same thing, and the degrees of freedom will also change. Does that make sense? Okay. Okay, so find that chi-squared statistic. So first find the expected values. Okay, so we have the A/B category, the C category, the D/F category. And then we have the most or always seatbelt wearers or the rarely never seatbelt wearers. So what is the row total for that first space?
1534.
5034. Column total is
1847.
Over.
2194.
You get the idea?
Yeah.
Okay. I got 1,292.56. How about the next one over? How about the ABs and the not wearing their seatbelts?
1534 times 345. 2192.
And for that one, I got 241.44. Based on how you round, these numbers might not add up exactly to the other totals, but they should come close. Does that make sense? Okay. How about this C category? What's the row total?
18. Oh. 550.
553, okay. Column total?
1847.
1847 out of, okay. I got 465.96. how about the next one?
405.
553,
Oh, sorry.
times 345, right? Over what?
190.
Anybody dare to say what they got for that?
87.04.
I got 87.04? Yeah, okay, yep. I thought she said 37 as well. Yeah, that wasn't just me. Yep. And the last one, we have row total, which is 105. Column total is 1847 over 2192, which is, I got 88.47. And the last one, row 105, column 345 over 2192, which is, I got 16.53. So do those numbers seem different than what you observed?
Yes.
Do you think yes? Okay. So, and the fact that you think that's true means your chi-squared probably should be big, okay? So let's write down what the chi-squared is. Chi-squared is observed minus expected squared over expected. So what's your first observed?
1292.56.
That's your first expected.
13.
Your first observed is the 1354, but then minus 1292.56 squared over, I understand it sucks to write this. Who comes next?
180.
Minus,
241.44.
I know, and then 428, right? Minus 465.96 squared. And just keep going, plus 125 minus 87.04 squared over 87.04 plus 65 minus 88.47 squared for 88.47, and then finally, goodness gracious, 40 minus 16.53 squared over, You can see this is going to get tedious really quickly, right? That's why we mostly did 2 by 2s, because they're just so much easier. But it makes sense that you're going to, in life, often have more than just 2 categories for people, right? Okay, and this comes out to be humongous. It's 77.776. This is what I got. Okay. So looking at that, find a p-value or p-value range. So first of all, what's your degrees of freedom? 2. Yep. There's 3 rows and 2 columns. That's 3 minus 1 times 2 minus 1, right? Okay. So look in your DF equals 2 row, and then look and see what's the biggest chi-squared that's shown there. Yeah, and you had like 70 something, right? So your p-value is less than 0.001. This is the one where Excel finds it. It just tells you it's 0 because it's so small, okay? So if you plug it into Excel and it gives you like something e to the negative whatever, that basically means that they're saying it's effectively 0, okay? Do you guys know what that e to the negative notation means?
Is it scientific notation?
It's scientific notation, yes. If Excel gives you like 5.4 e negative 3, yeah, it's 5.4 times 10 to the negative 3, or decimal back 3 places. That's what it means though, okay?
Yeah.
So, I don't know, I mean, they must use e because they'd have to otherwise have the mathematical symbol there. I mean, I think,
Yeah.
and also if they had a 10 there, it'd be confusing, right? So it's 5, 4, 1, 2, 3.
Oh, I was thinking E for exponent.
E for exponent probably is right, yeah. So 0.0054 would be what that would mean, okay? So if you get that, don't freak out, like it's, often if you get that, if you click on the cell in Excel, it'll show you like what the number is above, like in the little display thing. Okay, so since your p-value is effectively 0, that means that H naught is definitely out the window, right? Yeah, so since p is less than 0.001, or, I mean, that means p is less than 0.05 as well, right? You reject H naught because it's super unlikely. You accept HA. So what does that tell us about grades and seatbelt use? Yep, typical grades. And seatbelt use are related. Okay. So I think you get the idea. You don't do very many examples of these to, like, you get the idea of how they work. You realize it's just super tedious to punch those numbers in. Does that make sense? Okay. And a couple more things, and then we'll be done. So statistical significance and sample size. So a big difference might not be statistically significant if your sample is small. Does that make sense? Okay, so let's write that down. So seemingly large difference may fail to be statistically significant if the sample size is small. And you have a homework problem that talks about this. It gives you a table, and it says, find the chi-squared of this table. And you do it, and you get a chi-squared that's not very, like, exciting, and you're like, okay, I failed to reject H naught. Then you take the table, and you multiply everybody by, like, 5, and you do the chi-squared again, and you get a chi-squared that's super big, and then there's a big statistical difference. So the point is that big sample sizes definitely affect this chi-squared thing, kind of like they did with other stuff as well, right? Okay. And on vein, other things that you should include, you should always, if you were like preparing a report that included this stuff, you should include your descriptions of probably your row and or your column percentages to kind of illustrate how big the differences are. And everybody loves a picture, right? So you could, I think bar graphs are much easier to look at than numbers, right? Although I would also say beware of bar graphs because sometimes people distort the scales and make things look like better or worse than they are to their own, like, to, you know, kind of prove their own point. You could also look at these observed minus expected squares within each of the cells and look at which ones are the biggest differences because they're the most influential things. And then you could also find confidence intervals for, like, the proportion of differences. We could look at, okay, what's the proportion of A to B people who wear their seatbelts? And we could have done that for, like, each category and then compared those to each other. So just general ideas. And because I'm going to make you do lots of 2x2s, I'm going to show you a shortcut method for finding the chi-squared for just a 2x2, okay?
Yes.
I know. It only works for 2x2, okay? So you can use it for any 2x2 that you see. Anything bigger you have to use those E things. I'm so sorry, okay? So here's the shortcut. So if this is your table, chi-squared is equal to n times AD minus BC squared divided by C1, C2, R1, R2.
Oh, those are multiplied together?
Those are all multiplied together, yep, and degree of freedom is 1. I put brackets there because all that stuff has to end up in your denominator, and to do that, that has to go in parentheses after your division sign. Does that make sense? So I put those there to remind you that when you punch this in a calculator, you push divide, parenthesis, and then all that stuff, okay? And a lot of times people have a hard time doing this formula because they try to do it in pieces and the numbers are humongous. So if you're gonna punch this in a calculator, you've gotta kind of go at it in one go. That's the best way. And if you have a Casio, I don't know how to make it work.
Use Wolfram Alpha.
Use Wolfram Alpha, that would work too. But you can't use Wolfram Alpha on your test, so, you know. Yeah, okay. So let's do that for this one. So chi-squared is equal to, so first is the n, which is like the total from your table. So what is that for this guy? 1186, and then times, so we've got AD, so that's 247 minus
461 times 165.
and then that is, I think, squared, right?
Yes.
Okay, all that over 478, right?
Yeah.
708, 412, and 774. Okay, and this should give you, if you punch it in, 0.017. That's that whole marijuana table we did from before. But it's faster because there's no need to find expected values, okay? And it only works for 2x2s. So I apologize, it doesn't work for more than that, but that's all I've got. So use this for any of your 2x2s to find your chi-squared. Okay, so I plan